But there are things that are like. I mean, I don't spend as much time as I do as a postdoc. Just working on one problem at a time or fooling around. I still do that a little bit, but yeah, as you advance in your career, some of the more soft skills. So math somehow front loads all the technical skills to the early stages of your career. So so it's as a postdoc, as publish or perish, you're incentivized to basically focus on proving very technical theorems to sort of prove yourself, as well as prove the theorems. But then as you get more senior, you have to start mentoring and giving interviews and trying to shape direction of the field both research wise and sometimes you have to do various administrative things. And it's kind of the right social contract because you need to work in the trenches to see what can help mathematicians.
The other side of the establishment, sort of the really positive thing, is that you get to be a light that's an inspiration to a lot of young mathematicians or young people that are just interested in mathematics. And it's like, it's just how the human mind works. This is where I would probably say that I like the Fields Medal, that it does inspire a lot of young people somehow. This is just how human brains work.
Yeah.
At the same time, I also want to give sort of respect to somebody like Grigori Perelman, who is critical of awards in his mind. Those are his principles, and any human that's able for their principles to like do the thing that most humans would not be able to do. It's beautiful to see.
Some recognition is necessary and important, but yeah, it's also important to not let these things take over your life.
Yeah.
And like only be concerned about getting the next big award or whatever. So again, you see these people try to only solve like a really big math problems and not work on things that are less sexy, if you wish, but actually still interesting and instructive. As you say, like the way the human mind works, it's we understand things better when they're attached to humans, and also if they're attached to a small number of humans. Like there's the way our humans mind is wired. We can comprehend the relationships between 10 or 20 people. Yeah, but once you get beyond that, like 100 people, like there's a limit. I think there's a name for it. Beyond which it just becomes the other.
Yeah.
And so you have to simplify the whole mass of 99.9% of humanity becomes the other, and often these models are incorrect, and this causes all kinds of problems. But so to humanize a subject, if you identify a small number of people and say these are representative people of a subject, role models, for example, that has some role, but it can also be too much of it can be harmful because I'll be the first to say that my own career path is not that of a typical mathematician. I had a very accelerated education. I skipped a lot of classes. I think I had very fortunate mentoring opportunities, and I think I was at the right place at the right time. Just because someone doesn't have my trajectory, it doesn't mean that they can't be good mathematicians. I mean, they may be mathematicians in a very different style, and we need people with a different style. And even if and sometimes too much focus is given on the person who does the last step to complete a project in mathematics or elsewhere that's really taken centuries or decades with lots and lots of building on lots of previous work. But that's a story that's difficult to tell if you're not an expert, because it's easier to just say one person did this one thing. It makes for a much simpler history.
I think on the whole, it is a hugely positive thing to talk about Steve Jobs as a representative of Apple, when I personally know, and of course everybody knows, the incredible design, the incredible engineering teams, just the individual humans on those teams. They're not a team, they're individual humans on a team, and there's a lot of brilliance there, but it's just a nice shorthand, like pi.
Yeah.
Steve Jobs.
Yeah.
Why?
As a starting point, as a first approximation. That's how you.
And then read some biographies, and then look into much deeper first approximation.
Yeah.
That's right. So you were at Princeton too. Andrew Wiles at that time.
Oh,
He was
yeah.
a professor there.
Mhm.
It's a funny moment how history is just all interconnected. And at that time, he announced that he proved the Fermat's last theorem. What did you think? Maybe looking back now with more context about that moment in math history.
Yeah, so I was a graduate student at the time. I mean, I vaguely remember, there was press attention, and we all had the same, we all had pigeonholes in the same mailroom, so we all check out mail, and like suddenly Andrew Wows's mailbox exploded to be overflowing.
That's a good metric.
Yeah. So yeah, we all talked about it at tea and so forth. I mean, we didn't understand, most of us still didn't understand the proof. We understand sort of high level details. In fact, there's an ongoing project to formalize it in Lean. Kevin Buzzard is actually.
Yeah, can we take that small tangent? Is it how difficult is that? Because as I understand the proof for Fermat's last theorem has like super complicated objects.
Yeah,
it's really difficult to formalize now.
Yeah, I guess you're right. The objects that they use, you can define them. So they've been defined in Lean. Okay, so just defining what they are can be done. That's really not trivial, but it's been done. But there's a lot of really basic facts about these objects that have taken decades to prove, and that they're in all these different math papers. And so lots of these have to be formalized as well. Kevin Buzzard's goal, actually, he has a 5-year grant to formalize Fermat's last theorem. And his aim is that he doesn't think he will be able to get all the way down to the basic axioms, but he wants to formalize it to the point where the only things that he needs to rely on as black boxes are things that were known by 1980 to number theorists at the time. And then some other work would have to be done to get from there. So it's a different area of mathematics than the type of mathematics I'm used to. In analysis, which is kind of my area, the objects we study are kind of much closer to the ground. I study things like prime numbers and functions and things that are within scope of a high school math education to at least define. But then there's this very advanced algebraic side of number theory where people have been building structures upon structures for quite a while, and it's a very sturdy structure. It's been very at the base at least is extremely well developed in the textbooks and so forth. But it does get to the point where if you haven't taken these years of study and you want to ask about what is going on at like level 6 of this tower, you have to spend quite a bit of time before they can even get to the point where you see something you recognize.
What inspires you about his journey? That was similar as we talked about, 7 years, mostly working in secret.
Yeah, yes, that is a romantic. So it kind of fits with sort of the romantic image that I think people have of mathematicians, to the extent that they think of them at all as these kind of eccentric, wizards or something. So that certainly kind of accentuated that perspective. I mean, it is a great achievement. Yeah, his style of solving problems is so different from my own, but which is great. I mean, we need people like that.
Can you speak to it? Like what in terms of like you like the collaborative?
I like moving on from a problem if it's giving too much difficulty.
Got it.
But you need the people who have the tenacity and the fearlessness. I've collaborated with people like that where I want to give up because the first approach that we tried didn't work and the second one didn't approach, but they're convinced and they have the third, fourth, and the fifth approach works. And I have to eat my words. Okay, I didn't think this was going to work, but yes, you were right all along.
And we should say for people who don't know, not only are you known for the brilliance of your work, but the incredible productivity, just the number of papers, which are all of very high quality. So there's something to be said about being able to jump from topic to topic.
Yeah, it works for me. Yeah, I mean, but there are also people who are very productive and they focus very deeply on, I think everyone has to find their own workflow. Like one thing which is a shame in mathematics is that we have mathematics. There's sort of a one-size-fits-all approach to teaching mathematics, and so we have a certain curriculum and so forth. I mean, maybe like if you do math competitions or something, you get a slightly different experience. But I think many people they don't find their native math language until very late, or usually too late, so they stop doing mathematics, and they have a bad experience with a teacher who's trying to teach them one way to do mathematics that they don't like it. My theory is that humans don't come. Evolution has not given us a math center of a brain directly. We have a vision center and a language center, and some other centers which have evolution has honed, but we don't have an innate sense of mathematics. But our other centers are sophisticated enough that different people we can repurpose other areas of our brain to do mathematics. So some people have figured out how to use the visual center to do mathematics, and so they think very visually when they do mathematics. Some people have repurposed their language center, and they think very symbolically. Some people, like if they are very competitive and they like gaming, there's a part of your brain that's very good at solving puzzles and games, and that can be repurposed. But like when I talk to other mathematicians, they don't quite think that. I can tell that they're using somehow different styles of thinking than I am. I mean, not disjoint, but they may prefer visual. Like I don't actually prefer visual so much. I need lots of visual aids myself. Mathematics provides a common language, so we can still talk to each other even if we are thinking in different ways.
But you can tell there's a different set of subsystems being used in the thinking process.
like they take different paths. They're very quick at things that I struggle with, and vice versa. And yet they still get to the same goal.
That's beautiful.
But I mean, the way we educate, unless you have like a personalized tutor or something, I mean, education sort of just by nature of scale has to be mass produced. You have to teach to 30 kids. And, if they have 30 different styles, you can't teach 30 different ways.
On that topic, what advice would you give to students, young students who are struggling with math? But are interested in it and would like to get better? Is there something in this? In this complicated educational context, what would you?
Yeah, it's a tricky problem. One nice thing is that there are now lots of sources for mathematical enrichment outside the classroom. So in my day, there were math competitions, and there are also like popular math books in the library. But now you have YouTube. There are forums just devoted to solving math puzzles, and math shows up in other places. Like for example, there are hobbyists who play poker for fun, and they for very specific reasons are interested in very specific probability questions.
Yes,
and they actually there's a community of amateur probabilists in poker, in chess, in baseball. I mean, there's math all over the place, and I'm hoping actually with these new sort of tools for Lean and so forth that actually we can incorporate a broader public into math research projects. Like this is almost doesn't happen at all currently. So in the sciences, there is some scope for citizen science, like astronomers. They're amateurs who would discover comets, and there's biologists, they're people who could identify butterflies and so forth. And in math, there are a small number of activities where amateur mathematicians can like discover new primes and so forth. But previously, because we had to verify every single contribution, like most mathematical research projects, it would not help to have input from the general public. In fact, it would just be time consuming because just error checking and everything. But one thing about these formalization projects is that they are bringing in more people. So I'm sure there are high school students who've already contributed to some of these formalizing projects, who contributed to MathLib. You don't need to be a PhD holder to just work on one atomic thing.
There's something about the formalization here that also, as a very first step, opens it up to the programming community too.
Yes.
The people who are already comfortable
Yes.
with programming. It seems like programming is somehow maybe just the feeling, but it feels more accessible to folks than math. Math is seen as this like extreme, especially modern mathematics, seen as this extremely difficult to enter area, and programming is not. So that could be just an entry point.
You can execute code and you can get results. You can print a hello world pretty quickly.
Yeah.
Like if programming was taught as an almost entirely theoretical subject, where you just taught the computer science, the theory of functions and routines and so forth, and outside of some very specialized homework assignments, you're not actually program like on the weekend for fun.
Yeah.
Or there would be as considered as hard as math.
Mm-hmm.
So as I said, there are communities of non-mathematicians where they're deploying math for some very specific purpose, like optimizing their poker game, and for them, then math becomes fun for them.
What advice would you give in general to young people how to pick a career, how to find themselves, like what they could be good at?
That's a tough question. Yeah, so there's a lot of certainty now in the world. I mean, there was this period after the war where, at least in the West, if you came from a good demographic, there was a very stable path to a good career. You go to college, you get an education, you pick one profession, and you stick to it. It's becoming much more a thing of the past. So I think you just have to be adaptable and flexible. I think people have to get skills that are transferable. Like learning one specific programming language or one specific subject of mathematics or something. It's that itself is not a super transferable skill, but sort of knowing how to reason with abstract concepts or how to problem solve when things go wrong and so on. Anyway, these are things which I think we will still need, even as our tools get better. And you'll be working with AIs more and so forth.
But actually, you're an interesting case study. I mean, you're like one of the great living mathematicians, right? And then you had a way of doing things, and then all of a sudden you start learning. I mean, first of all, you kept learning new fields.
Yeah.
But you learn lean. That's a non-trivial thing to learn. Like for a lot of people, that's an extremely uncomfortable leap to take, right?
Yeah.
A lot of mathematicians.
First of all, I've always been interested in new ways to do mathematics. I feel like a lot of the ways we do things right now are inefficient. I spend me and my colleagues, we spend a lot of time doing very routine computations or doing things that other mathematicians would instantly know how to do, and we don't know how to do them. And why can't we search and get a quick response and so on? So that's why I've always been interested in exploring new workflows. About 4 or 5 years ago, I was on a committee where we had to ask for ideas for interesting workshops to run at a math institute. And at the time, Peter Schulze had just formalized one of his new theorems, and there were some other developments in computer-assisted proof that looked quite interesting. And I said, "Oh, we should run a workshop on this. This would be a good idea." And then I was a bit too enthusiastic about this idea, so I got voluntold to actually run it. So I did with a bunch of other people, Kevin Buzzard and Jordan Ellenberg and a bunch of other people. And it was a nice success. We brought together a bunch of mathematicians and computer scientists and other people, and we got up to speed on state of the art. And it was really interesting developments that most mathematicians didn't know what was going on. That lots of nice proofs of concept, just sort of hints of what was going to happen. This was just before ChatGPT, but there was one talk about language models and the potential capability of those in the future. So that got me excited about the subject. So I started giving talks about this is something more of us should start looking at. Now that I'd arranged to run this conference. And then ChatGPT came out, and suddenly AI was everywhere. And so I got interviewed a lot about this topic, and in particular the interaction between AI and formal proof assistants. And I said, yeah, they should be combined. This is this perfect synergy to happen here. And at some point, I realized that I have to actually do not just talk the talk, but walk the walk. I don't work in machine learning, and I don't work in proof formalization, and there's a limit to how much I can just rely on authority and saying, I'm a well-known mathematician. Just trust me. When I say that this is going to change mathematics, and I'm not doing it when I don't do any of it myself. So I felt like I had to actually justify it. A lot of what I get into, actually, I don't quite see in advance as how much time I'm going to spend on it, and it's only after I'm sort of waist deep in a project that I realize by that point I'm committed.
Well, that's deeply admirable that you're willing to go into the fray, be in some small way a beginner, right? Or have some of the sort of challenges that a beginner would, right? So new concepts, new ways of thinking, also, sucking at a thing that others, I think in that talk, you could be a Fields Medal winning mathematician and undergrad knows something better than you.
I think mathematics inherently, mathematics is so huge these days that nobody knows all of modern mathematics. And inevitably we make mistakes, and you can't cover up your mistakes with just sort of bravado and because people will ask for your proofs, and if you don't have the proofs, you don't have the proofs.
God, I love math.
Yeah. So it does keep us honest. You can still, it's not a perfect panacea, but I think we do have more of a culture of admitting error because we're forced to all the time.
Big ridiculous question. I'm sorry for it once again. Who is the greatest mathematician of all time? Maybe one who's no longer with us. Who are the candidates? Euler, Gauss, Newton, Ramanujan, Hilbert.
So first of all, as mentioned before, like there's some time dependence.
But on the day.
Yeah, like if you plot cumulatively over time, for example, Euclid is one of the leading contenders. And then maybe some unnamed, anonymous mathematicians before that. Whoever came up with the concept of numbers.
Do mathematicians today still feel the impact of Hilbert? Just directly of everything that's happened in the 20th century.
Yeah, Hilbert spaces. We have lots of things that are named after him, of course. Just the arrangement of mathematics and just the introduction of certain concepts. 23 problems have been extremely influential.
There's some strange power to the declaring which problems are hard to solve, the statement of the open problems.
Yeah, there's this bystander effect everywhere, right? Like if no one says you should do X, everyone just sort of mills around waiting for somebody else to do something, and like nothing gets done. So it's the one thing that actually you have to teach undergraduates in mathematics is that you should always try something. So you see a lot of paralysis in an undergraduate trying a math problem. If they recognize that there's a certain technique that can be applied, they will try it. But there are problems for which they see none of their standard techniques obviously applies. And the common reaction is then just paralysis. I don't know what to do. I think there's a quote from The Simpsons. I've tried nothing and I'm all out of ideas. So, like the next step then is to try anything, like no matter how stupid. And in fact, almost the stupider the better. Which, a technique which is almost guaranteed to fail, but the way it fails is going to be instructive. It fails because you're not at all taking into account this hypothesis. Oh, this hypothesis must be useful. That's a clue.
I think you also suggested somewhere this fascinating approach, which really stuck with me. I started using it and it really works. I think you said it's called structured procrastination.
No, yes.
It's when you really don't want to do a thing, that you imagine a thing you don't want to do more.
Yes.
That's worse than that. And then in that way you procrastinate by not doing the thing that's worse.
Yeah.
It's a nice hack. It actually works.
Yeah. There's, with anything, like, you've, psychology is really important. Like you talk to athletes like marathon runners and so forth, and and they talk about what's the most important thing, is it their training regimen or their diet and so forth. Actually, so much of it is actually psychology. Just tricking yourself to think that the problem is feasible, so that you're motivated to do it.
Is there something our human mind will never be able to comprehend?
Well, I guess a mathematician, I mean, like it's by induction, and it's there must be some sufficient large number that we can't understand. That was the first thing that came to mind.
So that, but even broadly, is there something about our mind that we're going to be limited, even with the help of mathematics?
Well, okay. I mean, it's like, how much augmentation are you willing? Like for example, if I didn't even have pen and paper, um, like if I had no technology whatsoever, okay, so I'm not allowed blackboard, pen and paper.
Right. You're already much more limited than you would be.
Incredibly limited. Even language, the English language is a technology. Uh, it's one that's been very internalized.
So you're right. The formulation of the problem is incorrect, because there really is no longer just a solo human. We're already augmented in extremely complicated, intricate ways, right?
Yeah.
So we're already like a collective intelligence.
Yes, yeah, yes. So humanity plural has much more intelligence in principle, on its good days, than the individual humans put together. It can also have less. Okay, but yeah. So yeah, the mathematical community plural is incredibly super intelligent entity. That no single human mathematician can come close to replicating. You see it a little bit on these like question analysis sites. So there's Math Overflow, which is the math version of Stack Overflow, and like sometimes you get like this very quick responses to very difficult questions from the community, and it's a pleasure to watch actually as an expert.
I'm a fan spectator of that of that site, just seeing the brilliance of the different people there. The depth of knowledge some people have, and the willingness to engage in the rigor and the nuance of the particular question. It's pretty cool to watch. It's fun. It's almost like just fun to watch. What gives you hope about this whole thing we have going on, human civilization?
I think the younger generation is always like really creative and enthusiastic and inventive. It's a pleasure working with young students. The progress of science tells us that the problems that used to be really difficult can become like trivial to solve. I mean, like it was like navigation. Just knowing where you were on the planet was this horrendous problem. People died. Or lost fortunes because they couldn't navigate, and we have devices in our pockets that do this automatically for us. Like it's a completely solved problem. So things that seem unfeasible for us now could be maybe just sort of homework exercises for me.
Yeah, one of the things I find really sad about the finiteness of life is that I won't get to see all the cool things we create as a civilization, that because in the next 100 years, 200 years, just imagine showing up in 200 years.
Yeah, well, already plenty has happened, like if you could go back in time and talk to your teenage self or something, I mean, and just the internet and now AI. I mean, again, they're beginning to be internalized, and so yeah, of course, an AI can understand our voice and give reasonable, slightly incorrect answers to any question. But this was mind blowing even 2 years ago.
And in the moment, it's hilarious to watch on the internet and so on, the drama. People take everything for granted very quickly, and then we humans seem to entertain ourselves with drama. Out of anything that's created, somebody needs to take one opinion, another person needs to take an opposite opinion, argue with each other about it. But when you look at the arc of things, I mean, just even in progress of robotics, just to take a step back and be like, wow, this is beautiful that we humans are able to create this.
Yeah, when the infrastructure and the culture is healthy, the community of humans can be so much more intelligent and mature and rational than the individuals within it.
Well, one place I can always count on rationality is the comments section of your blog, which I'm a big fan of. There's a lot of really smart people there, and thank you, of course, for putting those ideas out on the blog. And I can't tell you how honored I am that you would spend your time with me today. I was looking forward to this for a long time, Terry. I'm a huge fan. You inspire me. You inspire millions of people. Thank you so much for talking.
Thank you. It was a pleasure.
Thanks for listening to this conversation with Terence Tao. To support this podcast, please check out our sponsors in the description or at lexfriedman.com/sponsors. And now, let me leave you with some words from Galileo Galilei. Mathematics is a language with which God has written the universe. Thank you for listening, and hope to see you next time.